So hi everyone. My name is Emmanuelle Muhlethaler, and I'm a senior computer vision researcher here at Intuitive, and I'm gonna talk about how we used a deep neural network to solve a very specific problem of 3D point cloud compression and centerline estimation. So first, a little bit of context. So as Emmanuelle already mentioned, 22 to 28% of polyps are missed during the colonoscopy procedure. And for a number of reasons, among which the fact that the polyps never appear in the field of view of the endoscope camera. So here you have a computer simulation of a colonoscopy, and if you look at it, you can see that part of the inner surface of the colon is not inspected, either because parts of it are hidden behind the structure of the colon, or simply because of the orientation of the camera. And if you look at it like this, it's sometimes difficult to estimate how much is missed. Sometimes there is a region that might look hidden, but it's not really clear if you inspected it in the past or not. And what we want to do is to be able to measure and to quantify and measure how much of the inner surface of the colon is inspected during the colonoscopy. So we define the coverage as the percentage of the percentage of surface that was inspected during the procedure. So 100% coverage means that the entire colon was covered. So how can we measure something like this? How can we estimate the coverage? One way to do it is to use the output of the SLAM algorithm that Emmanuelle presented. So if you run SLAM on a video of a colonoscopy, you will get as output a 3D model of the colon, and unless the coverage is perfect, you will have holes in this 3D model. And the question now is, how do we get from this output of SLAM to an estimation of where the holes are and what their surface is in order to be able to estimate the coverage? So that's what I'm going to talk about now, this part. How do we go from the outputs of SLAM to an estimation of the coverage? So what are we exactly trying to solve here? So let's say that someone tells you that he took a video of an airplane and run SLAM on it and 3D reconstruction, and he got this point cloud. Okay, so when you look at this, you immediately see that probably stayed only on one side of the airplane, and that part of the point cloud is actually missing. Part of the airplane is missing. Yeah, he didn't go all around it. He just took a video on one side of the airplane. So let's. So yeah, so what you could guess, yes. So you might want to guess what is the complete point cloud, but of course it will be a guess. If one of the engines is missing on the other side, you have absolutely no way to know that. But you can try to give the best guess of what the complete airplane should look like. And if you try to do it, you might get something like this. And this is basically what we're trying to do. We have a point cloud of the, oh, sorry. Oh, shit. Sorry. We have a point cloud of the reconstructed colon, and we try to guess what do the missing surface look like. Okay, so the name of this problem is called, it's a 3D point cloud compression. And it's an area of active research. And if you read a paper published in the field, you will typically get this kind of comparison, where you have a different network, different algorithm, that the comparison of the different algorithm on a data set of airplanes and chairs and cars and things like this. And you have metrics, and everybody is training the network on this kind of very big data set made of this kind of objects, and everyone tried to beat the state of the art. And our problem is that we're not really interested in planes and cars and chairs. What we want is to guess what the missing surface are of colons. So we might want to train one of these algorithms on our own data set made of colons with holes. So the question is, what kind of data set do we have? So this specific paper, the network that was trained in this paper was trained on more than 30,000 models of this kind of shapes. What do we have? We don't have 30,000 models of colon. We have a handful of them. I put here 3 of them. So here the two on the left are a 3D model of the colon that we extracted from CT scans, and the one on the right is a synthetic model of the colon that was used to generate the kind of video that I showed you at the beginning of this talk. So it's very time consuming to extract this kind of mesh from a CT scan, and there is absolutely no way in the world that we could get anywhere close to 30,000 examples of this. So what can we do? If you look at this, you can see that there's quite a lot of variation between the shape of different columns. However, if you look at a small segment of a column, then the difference between different columns is much smaller. For basically what you have a tube with some structure. It can be a little bit curved or straight, but on this scale, the difference between 2 different columns is much smaller. So we can try to leverage this, and that's what we did. So what we did is that we split these columns into segments of different sizes. We added, so we randomly cropped some holes out of these segments. We added rotation, augmentation, scale, deformation, noise, and we managed like this from something that was from a very limited data set to generate a relatively varied data that we could train our network with. So what does it imply for our pipeline? So we now have a point cloud completion network. For now, I represent it only as this black box that takes as input a segment and not the entire column. And the question is, how do we go from this input of the entire reconstructed column to segmentation of it? This brings us to the notion of the center line. So the center line is a single line that spans the column, and that is roughly at the center of it, like is illustrated in this image. It's very closely related to the notion of a skeleton of a shape. Finding the skeleton of a shape in 3D is harder than what one might think at first. And it's still today an area of active research. Here are images from a paper published this year about a new skeletonization algorithm. So it's not a very easy problem, but for a simple model of the column, a closed mesh of the column, this is a synthetic data. There exists classic standard skeletonization algorithm that work pretty well. However, our input is not a nice 3D mesh of a column with no hole. It is a noisy point cloud with holes. It is basically the output of the SLAM algorithm. And on this kind of output of input, I mean, the classic skeletonization algorithm don't work so well, and they tend to fail. So what we can do is to try not to estimate the center line. We can try to use some clustering algorithm, and if we do this, we'll get this kind of segments, which are much noisier than the one I saw before. You have different sizes, like you have some very large segment here, a much smaller one here. They tend to overlap a little bit. Like for example, if you could imagine that if you would try to complete this point cloud, you would get some. It would consider this thing as a whole, right? Well, it's not really a whole; it's just an artifact of the segmentation. But it might be still it can still be okay to give this approximative segment to our point cloud completion algorithm, point cloud completion network, However, what we really want is an output that looks like this. Okay, so splitting the column into segments is not only a way for us to be able to build a rich data set, it's also a feature that we want from our output. Why do we want that? To be able to, we want to have a local estimation of the coverage. So what I show here is the reconstruction of the column that is split into segments, and each segment is for each segment we estimated the coverage. Okay, and the color of the segment is the segment are color coded with the coverage. So why do we want this? First of all, it's a much richer output than to simply give a single number for the entire column. If I say that the column was covered at 95%, it's not at all the same thing if every single segment has 95% coverage, or if most of it has 100% coverage and you have a few segments with 50% coverage. It's a completely different meaning. Also, if we want to run this algorithm in real time, to have a local estimation of the coverage allows us to be able to to alert the physician to the fact that there is a region where where the coverage is insufficient, and to redirect him to this region. So it's important for us to have a local estimation of the coverage, and for this it is crucial to have segments that are well defined, that don't overlap, and that have a consistent length. So we do need the center line. And because of this, we decided that our point cloud completion network will not only try to estimate the missing surface, but also estimate the center line at the same time. Okay, so I'm going to go now into this box and try to show you what our point cloud completion network look like. Okay, so one of the main characteristic of this network is that it has an input. It's its input and its output. So the input, we use that input not directly the segment, but we build a heat map that represents the input segment with the holes, and our point cloud completion outputs another heat map representing the segment with no holes and the center line. And then we have an extra step that we use in order to extract from this heat map the center line and the mesh. So just a few more words on these heat maps. Basically, the input heat map is some kind of distance map. You can see this is like a 2D version of it. So this is like a 3-dimensional matrix. If you would look at it in 2D, it would look like this. This would be, if this is the surface of the column, at the position of the surface, the values are 0. And as you get away from it, the values increase here to a maximum of 1. For the target, it's very similar, except that now, so still at the position of the surface, you have 0 values. At the position of the center line, you have 1s, and everywhere else things converge to 0.5. And so this is what our network outputs. And then we have an extra step where from this heat map, we extract the center line and the completed column segment. So how do we do this? We could try to just use a threshold, since the surface has value that are around 0 and the center line has value around 1. We could just threshold this heat map and we would get something like this and like this. The problem is that this solution lacks structure. What we get here are just point clouds, and what we want is for the center line to have a single connected path, and for the completed column segment, we want a mesh from which we can extract surface. We can estimate the surface. So instead of simply using a threshold, what we did is that we use this heat map as a speed map. So the maximum speed would be at the position of the center line here, and we simply look for the fastest path between one extremity and the other of the segment. And for the mesh extraction, we used a very well-known algorithm that is called mashing cubes, that basically extract mesh from this kind of 3D matrix where the position of the surface is equal to 0. So we need to modify it a little bit, but basically we use matching cubes. And so that's our algorithm. Now I'm going to show you a few results. So first of all, our test set. So this is we run this on a data set that we build the same way as our training set, from CT scans and synthetic data. We try to add, so what you have here is, this is the input, these are the estimated holes, this is the estimated center line. We added to it Gaussian noise that was very different from the noise with which we trained the network, just to see if it was robust to different kind of noises. Without noise, we got 3% mean absolute coverage error, and with the noise, we got 6%, which mean absolute coverage error, which is not so big. So how does it look on the actual output of the SLAM, which is what interests us? So I already showed you this result. Unfortunately, we cannot get metrics on this because we don't know what is there in the place where you have a hole. We don't have ground truth for that. However, we can visually inspect the result. So we can take a segment and look how the point cloud completion and centerline estimation did. So this is the input segment. This is the hole estimation, and this is the centerline estimation. And you can do it for all the segments. And it works. It works pretty well, even in cases where a very large part of the segment is missing, like here, where you have like a 50% coverage, and it managed to really reconstruct the surface in a way that looks very reasonable. We also try. So this is this output. This is an output of SLAM that was run on a rigid print of a column. We also tried to test it on the output of SLAM from a real colonoscopy video. And here again, even though the data looks very different from our training data, we got results that made a lot of sense. You can see here the input point cloud, the estimation of the holes, and the center line. And so that's it. So just to recapitulate, we started from a point cloud completion problem, and due to the specificity of our problem, we were led to create our own point cloud completion and centerline estimation network, and this can be used to estimate the coverage in 3D reconstruction of the column. Yeah, sure.
Some kind of a clustering algorithm to get the first segment.
Yeah.
Why not use smaller sections with the idea of looking at a tube kind of shape and a small segment?
I didn't understand. I'm sorry. Can you repeat?
If you look at a small enough segment, you can approximate a tube-like structure, right?
A tube-like
structure.
A tube-like structure. Okay. Yes, we actually did try once to fit, like to have to try to fit tubes, right? To have an algorithm that would fit a small tube to the reconstruction, and it was not working very good. I mean, it works sometimes. it fails very often. There are many cases. The thing is that the output of the algorithm has, I mean, I mean, in the easy case it succeeds, but there are many cases in which the shape is not the fit of the cylinder on it we get terrible results, and also it tends to be very slow.
Part of the pre-process for the input, take the cluster and try to look at the convex hull in the shape of the tube as your input, instead of the one that has overlaps that are create your own kind of holes in the structure.
Again.
As your input, you have
yes.
the cluster, the data cloud points, right?
The clustered what?
Cloud points.
Yes, yes.
So you said there's a lot of overlapping and structured holes within the cluster.
Yes, yes.
So how do you overcome that?
Yes, okay. That's a good question. So what we do is actually we run. So there are difference when we run it or try to do it online or if we do it off like at the end of the procedure. But basically, our network outputs this heat map. So what we do is that we get all the heat maps and we merge them all together. Okay, so then we have a big heat map from which we extract the center line and the mesh, and then with the center line we split the results.
You don't try to cover that in the pre-process.
No. So we estimate we do it, we fix it post-process, basically. We estimate the coverage for each of these segments, and then we merge everything together, and then we extract the center line and the mesh. Yeah.
So your original data comes from, the guy said before, is that like step maps and grayscale. You have an option to segment to identify different tissues and segment that.
Sorry, I apologize. I didn't understand.
Grayscale.
From grayscale, no. So no. From a CT scan. So the training data, it comes from CT scans from which we extracted the mesh.
Okay. So once from the CT scan, you have an option to identify different types of tissue in it.
The thing is that what we cared about is to have something that looks like the output of SLAM. And the CT scan, we don't have. The assumption is we don't have a CT scan. We have the output of the SLAM algorithm, and so we wanted to have a training set of shape that look like columns. So all the information that we can get from the CT scan are information that we don't assume that we will have, when we run SLAM on colonoscopy video. Okay, can you? Yeah, sure.